Well, we are going through various applications of the techniques we developed, and today we'll have a few more applications. The first one will be Bizu Theorem, and you already had it in home assignment last year, but let's redo it from the high-tech point of view. So it will be just for curves on the plane. Okay. So we have a curve. It will be a smooth curve. Of degree, say d. So it means that it is cut out by a single homogeneous polynomial of degree d, and then we claim, first of all, that the genus of this curve is d minus 1 times d minus 2 over 2. Right? For example, if degree is 1, certainly the genus is 0. If degree is 2, then genus is 0 as well. So it's a smooth quadric, is isomorphic to P1 by stereographic projection. And if degree is 3, then genus is 1. It's an elliptic curve. We know this. Okay, and the proof is immediate because we have the ideal sheaf of C embedding into the structure sheaf of the projective plane, and the quotient is the structure sheaf of our curve. But this ideal sheaf is generated by this single polynomial of degree d. So it has well, it's an invertible subsheaf in the structure sheaf, and it must be just of minus d. Okay.
А если он образуем полином степени d, почему o от минус d пишется?
Because it's a subsheaf of the structure sheaf, right? You could not possibly have an embedding from positive line bundle into this trivial line bundle.
Да, спасибо.
Okay. So then you can compute the Euler characteristic of the structure sheaf as Euler characteristic of the structure sheaf on the plane minus Euler characteristic of.
I'm sorry.
Yes.
I think you missed push forward.
Push forward
between OC.
Yeah,
in front of OC.
I understand. Yeah, but let me leave it as is, if you don't strongly mind. Okay. So now this is 1, and this can be computed well straightforwardly, because you remember that for an invertible sheaf, you only have either the zeroth cohomology, and it's some polynomial space, polynomials of degree d, if d is positive, or else if d is negative, then you can only have the top, that is second cohomology, and it is again some polynomials, but of degree d minus 3 in this case. Yeah, maybe remember we had this a month ago. So also, you know, the formula for dimension of homogeneous degree, whatever, d prime polynomials in 3 variables. in 3 homogeneous variables. So the answer will be negative d plus 1 times negative d plus 2 over 2. And again, you can check that it works in the basic examples, namely if d is say negative 1, then the corresponding invertible sheaf is absolutely cyclic. It has no zero cohomology, no first cohomology, no second cohomology, nothing at all. And the same for d equals minus 2. Yeah. So in general, chi of OPN twisted by d will be d plus 1 times and so on times d plus n over n factorial. Okay, so so we know this. Now we can subtract, and if we subtract, we get what we want, because we also know that this is 1 minus the genus of C, right? So there we are. And if C is not necessarily smooth, as was our assumption in the beginning, then 1 minus the Euler characteristic of the structure sheaf is called the arithmetic genus.
Где использовалась гладкость в предыдущем рассуждении?
Of C. Well, for example, this formula that the Euler characteristic is 1 minus genus. Yeah, when we produce those notions, we only dealt with smooth curves, right? And you can have something like this. Nodal curve. Well, so this is, so to say, P1 modulo. You glue two points like this. So there is a normalization map like this, new normalization, or resolution of singularities. So anyway, the arithmetic genus of this thing will be 1. So it can be realized as a cubic such thing is a singular.
А где нормализация была востребована в определении арифметического рода?
Cubic. Well, no. But by definition, the arithmetic genus is 1 minus the Euler characteristic. You don't need anything at all. Yeah, that's just definition. There it is. And if you use normalization, then there is another definition that the geometric genus is a genus of the normalization. So in particular, the geometric genus of this singular nodal cubic is 0. Okay, and you see in families, well, we already proved this theorem that the Euler characteristic of fibers is constant, or say locally constant in families. So the arithmetic genus is constant in families. For example, you can have elliptic curves, smooth cubics, degenerating into to a singular cubic. And in this family, all the arithmetic genera are the same one. But the geometric genus will drop when you specialize to the smooth cubic. Oh, sorry, to the singular cubic. Okay, so well, again, more generally, you have a singular curve C and its normalization C tilde, then the arithmetic genus is always at least the geometric genus, and the difference is the sum over all the points in the singular curve, the dimensions of the say, oh, sorry, it's new. Of new, or the push forward of the structure sheaf of the resolution modular the structure sheaf of the base. I mean, for almost all points, the new is an isomorphism, and so this quotient is zero dimensional. The summands only occur at the singular points of the base. Okay. So now
You mean stocks of this.
Yeah, the fibers of this sheet.
Sorry. Yeah, it's at the point. Yeah, right. Sorry. Well, let me put the small c here, though not very small, something like this.
Как это доказывается, формула?
Pardon me?
Как доказывается формула?
Well, just from the additivity of Euler casuistic, just immediately. Okay. So now this famous Bizu theorem. We have now two curves. So this is our projective plane. There is one curve like this. There is another curve like that. And we want to find the cardinality of their intersection, but they may intersect non-transversely. So we need to introduce the intersection multiplicity at various points, and say for a point in the plane, the intersection multiplicity at this point of our curves, say this was C and this was S, is equal to dimension of the structure sheaf of the ambient plane modulo the sum of two ideals, this curve and that curve. Okay, and certainly if your point is not a point of intersection, then this will be just zero. I mean, the two ideals will span the whole structure sheaf. So the theorem is that the sum over all the points. Well, I may write the intersection, but doesn't matter. I can sum over all the points in P2. The intersection multiplicities of those two curves at those points is the product of degrees of these two curves, and the proof is very short and simple. So, well, let us just introduce a shortcut for this quotient. Because the sum of ideals is an ideal, and hence this quotient is a ring, but it's a finite dimensional ring, right? It's supported only at the point of intersection. But by the way, I should have said from the very beginning that the curves do not have a common component. Well, where should I say this? Maybe if the intersection is finite, then this formula holds true. So there's a finite dimensional ring, and let us denote it just the intersection of two curves. And well,
А почему это же все-таки утверждение, а не определение? Это же
what exactly? I'll just define. The point is that this intersection is only a scheme. It's not an algebraic variety in general, because it might have nilpotence. This ring may have nilpotence. If the intersection is not transversal, then the quotient will be a ring with nilpotence. And so it is, well, we'll study schemes in a couple of weeks, but so far we don't have language to speak about this.
Вот еще вопрос. Почему берется, например, сумма, но не произведение?
Well, I don't know. You wanna? We will have the product of ideals in a moment too. But the problem we are studying at the moment is the intersection of curves. The intersection of curves corresponds to the sum of ideals. Is a scheme with nilpotence. If the intersection is not transverse.
Maybe you can illustrate this with an example.
I didn't quite hear you. Can I illustrate this? That's what was the question.
Yeah, just some easy example.
Yeah, certainly you can have like a parabola tangent to the line, and then this will be k of x modulo x squared, like this. So this will be s. Okay, but again, we don't need formally we don't need any discussion like this. It is just a notation shortcut. So then again, as before, as when I computed the genus of a smooth curve, we need some explicit resolution to compute the dimension of this. So well, this is a zero-dimensional scheme. So the dimension of O is just the Euler characteristic of O, and it can be computed via resolution. Locally free resolution on P2. So let's write this resolution. Well, we have sorry. So I have this structure sheaf, and certainly it's the quotient of the structure sheaf plane, and there you have those two ideals, JC plus JS, and inside the structure sheaf of P2, those ideals certainly do intersect. So the sum is not, let me ignore this and let me write as direct sum. And I know that this is O of minus degree of C, and this is equal to O of minus degree of S. And now there will be a kernel of this map, and this kernel will be just in the intersection of ideals. In other words, the product, as Sergey suggested. So the product is, well, let me write JC intersection with JS. Since they don't have common components, they are relatively prime, and so their intersection will be isomorphic to O of negative DC minus DS. Okay, and this is the desired exact sequence. Okay, so from here, the desired Euler characteristic of intersection of our curves is the Euler characteristic of P2. So it's 1 plus the Euler characteristic of O minus DC minus DS minus Euler characteristic of O of minus DC minus the Euler characteristic of O of minus DS. Okay, and we already know all those Euler characteristics. We wrote it down somewhere in the middle of this page. Yeah, in the middle of the first page. So if we apply this, then you will get the desired degree of C times the degree of S. Yeah. That's it.
А вот как мы так быстро поняли, что пересечение идеалов это O от минус DC минус DS?
Just because they're relatively prime, so their intersection. So if locally your ideal is generated by the equation of C, and another one is generated by the equation of S, then their intersection will be generated by the product of these two equations. Yeah, so the degree will be the sum of degrees. Right? Maybe right here, since the ideal of C and the ideal of S are relatively prime.
Извините, а где было использовано то, что конечное число точек пересечения CSS доказательство?
Well, otherwise, if they have a common component, then the ideals are not relatively prime. So either they have finitely many intersection points, or they have a component in common. Yeah, because the intersection is Zariski closed, and if you have infinitely many points, the Zariski closure must be of dimension at least 1. So it must be a common component. Okay. Okay. So now for something completely different, there is the theorem called Riemann, Birkhoff, Grothendieck theorem. Or in other words, classification of vector bundles that is the same as locally free sheaves on the simplest projective variety on the projective line. And somehow this topic is very, very interesting and important. I mean, not exactly this, but vector bundles on algebraic varieties, already on algebraic curves. So if for P1, the answer is explicit and elementary, and I will explain it in a moment. But already starting from elliptic curves and higher genera, the answer is more and more involved. And so, first of all, the answer for projective line will be discrete. So the isomorphism classes of vector bundles form sort of code in some integral lattice. Well, depending on the rank of your bundle. And starting for any other curves, the isomorphism classes of vector bundles will have continuous parameters. So the answer will be not discrete. It will be so-called moduli stack of vector bundles. And this moduli stack is really the central object of the biggest part of modern mathematics. Say it's called geometric Langlands program. So maybe I should stop before it's too late. But it is really a very, very important subject. Also, you may grow in some other direction, not a curve of higher genus, but projective space of higher dimension. And then again, starting from P2 and P3 and so on, you will have continuous parameters in vector bundles. So there will be some interesting moduli space of vector bundles on projective varieties. And this is again a very, very important subject. They're studied from the point of view of mathematical physics. They're called instantons or gauge equivalence classes of anti-self-dual connections. So this is an enormous field of modern mathematics and mathematical physics. Okay, but in this simplest case, the answer is also simple. And it was, in a sense, obtained by Riemann, and then from another point of view by Birkhoff, and then Grothendieck in 1957 gave a very, very elementary and simple proof. And this I will explain now. Maybe, well, let me say only one word. Why is it called Riemann-Birkhoff? Because this set of isomorphism classes of vector bundles on, say, P1, in fact, on other curves as well, it is naturally in bijection with GL n of the field K formal Laurent series modulo GL n with coefficients in the ring of polynomial in T inverse. Okay, and also these are double cosets GLN with coefficients in the ring of Taylor formal series, like this. And this is something like Bruat decomposition or Cartan decomposition. I don't know, Rivasava decomposition. There are many versions of this. So these are double cosets of some group modulo its sort of parabolic subgroups. This was first studied by Riemann well, for him, it arose from solution of some differential equation. So it was close to some Riemann-Hilbert problem. And for Birkhoff too. And then Grothendieck somehow formulated it and proved it just in terms of algebraic geometry. Okay, so first of all, the answer is as follows. So any vector bundle is just the direct sum of line bundles O1 of di, and say this di must be a signature, so to say, uniquely defined signature. D, this is D1, and it's not smaller than D2, not smaller than so on, not smaller than DR. So R is the rank of our bundle. Okay, so these are certainly integers and non-increasing sequence of integers. I mean, if they are all positive, then that's called partition, right? But now they're not necessarily positive. Some may be positive, some negative, and this is called signature. The terminology is due to Hermann Weyl. Okay, so now let's go and prove it. First of all, let's prove uniqueness. So given V, we have to determine those D1 plus D1 plus DR. And say, how can we determine D1? Any suggestions? The highest degree sum of all. How can we determine it? Any suggestions? No. So you know that if you take V and twist it by negative D1, then it does have some global sections. But if you twist it even more, then there will be no global sections at all, right? So D1 is defined like this. I mean that maybe I should say that if you twist it more and more, it will have 0 global sections, and if you twist less and less, it will have non-zero global sections. And the boundary is exactly at D1. Okay, well, namely the dimension of these global sections is the multiplicity of D1 in the signature okay. So now we have to determine, well, suppose that the signature is like D1 equals D1 equals so on, D1, and then you have strictly smaller D2. So
you mean dimension of what?
On. Dimension of what? Well, dimension of this global section.
Okay.
So how to determine D2? Any suggestions?
Again, twist it and see the dimensions.
Right. Because if you twist it by d1 plus 1, then the dimension will be, well, let's say this is m, m 2m, right? And so on. So I mean dimension of gamma p1. Maybe I should call it m1. Well, that's not d2. Sorry, I don't know how to say it. That's not d2. How should I denote it? I don't know. Any suggestions? Maybe like this.
На двойку умножили.
Because when I, well, the dimension of say gamma of p1 of 1 is 2, right? So that's why I multiply by 2. Okay, so and so on. It grows linearly, but then at some point I get to.
Что такое multiplicity of D1? Мы написали, что размерность сечения есть в multiplicity D1.
Yeah, how many entries of the signature are equal to the first one, and then at some point you get strictly smaller. Okay, so when I twist it by negative d2 finally, like this, then it becomes whatever d2 d1 minus d2 times m1, and then plus m2, yeah, and so on. So you know what is d2 and what is its multiplicity. Okay. So when you twist your vector bundle by sublon bundles, then the behavior of sections is just this. First I have 0, then it starts growing linearly, then at some point it grows faster, then at some point still faster, and so on. And this happens at d1, this happens at d2, and so on. Okay, so this proves the uniqueness.
Можно вопрос?
Yes.
А изоморфизм векторных расслоений — это не то же самое, что изоморфизм пучков?
Oh yes, absolutely. It is.
То есть нет тоже.
Absolutely, it is the same. These are just synonyms. Vector bundles and locally free sheaves are just synonyms. We had some exercise about this last year.
Ну, мы же можем взять, скажем, на кривой какое-нибудь одномерное векторное расслоение. Мы можем взять одну точку, можем взять другую точку, скажем, C1 и C2, и взять пучки O от C1 и O от C2.
Right.
Они не изоморфны обычно.
If your curve has genus 1 or more, then these guys will be not isomorphic. But if your curve is P1,
мы на P1.
then they are isomorphic. Yeah. So where it is very important, it only works for P1. Doesn't work for higher genus, doesn't work for higher dimension. Only for P1.
Спасибо.
Okay. So let's go prove existence. Okay. So well, we are free to twist our vector bundles. so our claim for V is equivalent to the claim for V twisted by D, and we choose this twist just for the convenience sake. We choose this twist as follows. That the global sections of V is 0, but the global sections of V of -1, oh sorry, this is not 0, but this is 0. So V has some sections, but if you twist it a little bit, it has no sections at all. Okay.
Если я понял, вот в последнее утверждение выберем D так, чтобы сечение расслоения ню было от P1 отлично от нуля, а ню от минус 1. А где в нем D? Где в этих сечениях D зарыто?
Well, we and replace V by V of D.
Понял,
Okay.
спасибо.
Fine. So take a section sigma, well, no zero, and then we have a subsheaf a structure sheaf embeds into V, and then I have some quotient, say V prime. Okay, and the first claim is that V prime is locally free. Yeah, because you see, in principle, it can happen. For example, V could be of rank 1, and say it could be like O of 2, yeah. And then you take any section, you get an embedding from O to O of 2, but you know that in the quotient you will have just two-dimensional torsion sheaf. Okay, but I claim that it is locally free. That is has no torsion. And indeed, so let's T in V prime be torsion subsheaf. Yeah, maybe let me call this also pi. Okay, then the pre-image of this torsion subsheaf is a subsheaf in V, and V has no torsion, right? So this is a locally free guy, a torsion free subsheaf, and it's locally isomorphic to O P1, right? Because the pre-image of 0 in V prime is O P1, yeah, just by definition. It's the kernel of pi. And now we take the pre-image not quite of 0, but of torsion sheaf. So away from the support of this torsion sheaf, we get O P1. But as a whole, it's necessarily a line bundle, an invertible sheaf, but which is supposedly strictly bigger than OP1. So the pre-image of T is some line, well, invertible sheaf L that contains OP1, but is strictly bigger. Okay, fine. Hence, L is isomorphic to some positive line bundle. I don't know how to say it. D or C for positive C. Oh, maybe N. Maybe N. Let me put N for positive N. Okay, but then it means that the global sections of P1 with coefficients in L of -1 is not 0, and it implies that the global sections of P1 with coefficients in V twisted by -1 is not 0, and this contradiction. We assumed this was 0, if you remember. Yeah, this was our assumption. The global sections of twisted V is 0. Okay, so we proved that the quotient sheaf V prime is locally free. Nice. And so V prime is locally free of rank smaller. So by by induction assumption, V prime is the direct sum of line bundles, like this. Fine. And we know
а
that
R маленькое это D, которое было, или это другое?
R is the rank. That's what you asked?
А ню было ранга D или R? Изначально просто в определении мы не давали.
The rank is R. D is degree. Rank is R. Okay.
Can I ask how we see that the torsion subsheaf is 0 in the proof?
Well, assume there is some torsion. Then its preimage must be an invertible sheaf. The preimage lies in V. V is torsion free, right?
Mm-hmm.
So any subsheaf in V is also torsion free. The preimage lies in V, so it's torsion free. Okay.
Yeah, but some J, why it is torsion free? Why some J is its preimage is torsion free, but
right?
But J may have torsion.
I don't know, probably it's T, yeah. What is called J is T. So suppose we have a non-zero torsion subsheaf T, then its preimage is a torsion-free subsheaf, and it is subsheaf of rank 1, right? The invertible torsion-free subsheaf. Okay. And it contains, if this T was not 0, then this torsion-free subsheaf L strictly contains the structure sheaf OP1. Yeah, because this OP1 was the 0 of this kernel of pi. Right? Okay.
Yeah.
So if it strictly contains OP1, it must be a strictly positive line bundle. So when you twist it by -1, it still has section. But it contradicts to our assumption. We assume that V of -1 does not have any global sections. Okay.
Okay, thanks.
So where are we? We know that the quotient sheaf has this decomposition into line bundles by induction, and we know that all those summands are non-positive. since the global sections of we know that there are no global sections. Yeah, so we have 0 global sections of P1 with coefficients V of -1, and well, there is this exact sequence for the quotient V prime of -1, and then there will be this co-boundary morphism into the first cohomology P1 with coefficients of with the structure sheaf twisted by -1, but this is 0. Okay, so this is also 0. And it implies that all those summands are non-positive. Okay, and now we will prove that our exact sequence 0 to O to V to V prime to 0 splits. Okay, so V is O plus V prime. Well, we know that V prime is the direct sum of line bundles, and we just add one more line bundle, and there we are. So let's dualize it. We'll have 0 to V prime dual to V dual to O dual, but O dual is again O. And now this thing V prime dual is the direct sum of of negative di's, and those negative di's are all non-negative, right? We had that di's were all negative, so negative di's are all positive. Okay, fine, but this implies that the first cohomology of V prime dual vanishes. Okay, and hence, if you write down long exact sequence of cohomology for this short exact sequence, it will be the global sections of V with coefficients with V dual surject onto the global sections with coefficients in O. Okay, and here we have the 1, and you may take it pre-image, whatever, say alpha goes to 1, and then you will have a section here, namely 1 goes to alpha, and it splits this is a short exact sequence, and the dual one is split as well. It's the dual split. Okay, so we're done. Okay.
Could you say I missed some moment? Why first cohomology of this direct sum is 0? This is just because
all the summands are positive line bundles, and the positive line bundles do not have first cohomology. Right?
It is important that they are on P1.
Absolutely, yes, absolutely.
But if we have another curve, say, and the same.
For example, say on elliptic curve, the structure, well, in fact, on any other curve, the structure sheaf always has non-zero first cohomology. It's only for genus 0 for a projective line that the structure sheaf has no first cohomology. For any other curve, the structure sheaf will have first cohomology.
Okay.
Yes, so we used this very essentially. Okay. Yes.
It was just that I wanted to notice that the dual in general it is not possible to dualize a short exact sequence and hope that
absolutely, yeah, but here you see it consists of locally free sheaves. That's what important. Yeah, we took some pain to prove that V prime is locally free.
Yeah, but
and for locally free sheaves, you can dualize because this is locally split, as we argued last time.
But are there any higher x local x?
No, locally no. For locally free sheaves, if you have a short exact sequence of locally free sheaves, then it is locally split. It is locally direct summon.
I see. Okay, thank you.
Just because when I have a projection from a free module to a free module, so it's surjective, then it has a section. So it's always a projection onto direct summon for free module. Okay.
Okay.
Fine. So now the next important topic will be extension of rational morphisms. Of codimension 2. So what is the setup? We have a smooth irreducible separable variety.
Какое значение вот эта предыдущая теорема имеет?
Grothendieck theorem?
Да.
Well, as I mentioned, it can be viewed as a classification of double cosets in the loop group of GLN. And in fact, Grothendieck proved this for arbitrary reductive group, like orthogonal group or symplectic group or G2 or E8. This is just one thing. And also it has important applications for like Riemann-Hilbert theory, like classification of differential equations.
На другие группы есть обобщение?
Pardon me?
На другие группы есть обобщение?
Yeah, that's what I say. Yes, you can similarly classify double cosets like this for arbitrary group G, reductive group G, in place of GLN, and it will be classified by the lattice of dominant co-weights. So for GLN, dominant co-weights are just signatures, but for other groups, it will be some other cone in some integral lattice.
Спасибо.
Okay. Okay. So we'll have a smooth separable variety, and it will map into some other projective variety, or maybe even proper variety. So we'll have a rational morphism. And what does it mean? If you remember from some old home assignment, it means that there is some open subset U inside here, and a regular morphism, say F, from U to Y, but it does not necessarily extend to the whole of X. Okay, but let's take this open subset U to be the domain of this F. So some maximal open subset where F is regular. So U.
Почему такое существует максимальное множество? Почему не бесконечно нельзя увеличивать?
Well, maybe if you wish, because of quasi-compactness. So you take all the open subsets where F is regular, and then you take their union, and this union is another open subset. Okay, and then the claim we're after is that the dimension of the complement is at most dimension of X minus 2. So in other words, you can the rational maps extend through divisors.
Я имею в виду, да, множество как бы ограничено сверху, но я имею в виду, что множество U, оно ограничено сверху, как бы, что квазикомпактностью, но почему бесконечно нельзя добавлять к нему какие-то регулярные области, в которых будет регулярно функция F, вот это не очень понятно. Ну, по чуть-чуть, например, но бесконечное количество раз.
Right. I don't really understand what's the problem. So I claim that, well, if you wish like this, I claim that there is an open subset U such that the F on this U is regular, and that the dimension of the complement is at least the codimension of the complement is at least 2. That's what I claim.
Понял.
There is an open subset U. F is regular on this U, and the codimension of the complement is at least 2. Okay. So let's prove this. First of all, we can immediately reduce it to the case of projective Y. So Y can be taken projective, since by the Chow lemma, Y is dominated by say Y prime, but that is projective, and go to Y. This is regular and birational. Okay, and since it's birational, then our map from X lifts here. Yeah, just because this pi is birational, so it can be inverted in the category of rational maps.
Но мы же F определили, извините, пожалуйста, мы же F определили на подмножестве U каком-то, а сейчас мы говорим, что оно определено на всем X.
But it is rational. Once again, it's rational. So it's by definition, it's defined on the open subset. So if we prove it for Y prime, then we prove it for Y. Okay, and Y prime is projective. So we can assume that Y is projective. Okay. So now, so once again, from now on, Y is project. Okay, and now we have this X containing U. This U goes to Y, and then take gamma, the Zariski closure of graph. Sorry, graph of F in the product X times Y. So the graph of F it lies in U times Y, and we take its closure in X times Y. Okay, so now we know that the projection pi from gamma to X is birational, since it is isomorphic over U, right? And if this projection were an isomorphism, then we would be in business, right? But unfortunately, it's not necessarily an isomorphism. So it may have some big fibers. So we have to estimate this bad set of big fiber. So let's set this bad set is the set of points in gamma such that the dimension of the fiber like this is positive. Okay, the bad set of higher dimensional fibers. Okay, so it is a subset of gamma, and by the upper semi-continuity of dimension of fibers, this B inside gamma is closed. Okay, and hence the projection in X is also closed, right? Because Y is projective, so the morphism, this pi is projective. Okay, and by definition, our good open set U lies in the complement of this open subset. And let's denote this V. Okay, and now let's prove the key claim that U is exactly this, is exactly V. So U was the maximal open set where our morphism F was well defined, regular. I mean, I want to prove that our morphism F is regular on this U. So that is, F is regular on the whole of V. Okay, fine, and let's prove this. We set gamma prime is the preimage of V, and hence we have projection pi from gamma prime to V. Again, it is projective with finite fibers by the very definition, because we removed all the dimension 1 or higher fibers, and hence by our key lemma proved I forgot last time or last week, but not very long ago. It means that this pi from gamma prime to V is finite. So projective morphism with finite fibers is necessarily finite. Okay. But we know that X was assumed smooth. So V is smooth and hence normal. And well, how to say it? Gamma prime is the normalization of V in well, in the field of fractions of this ring, but V is normal, and the field of fractions is the same. Hence, gamma prime is just V. Okay, so I mean, well, maybe I shouldn't say this. Maybe I should say that pi is an isomorphism from gamma prime to V. Fine. So we proved what we wanted, that our F is regular on V. Very good.
Видите, не совсем понятно. Вот в основном утверждении, вот
Yes.
предыдущее за леммой, мы доказываем, что π это изоморфизм. Почему это необходимо доказать для утверждения нашей исходного утверждения?
Well, but then gamma, if pi is an isomorphism, then gamma prime really is the graph of F restricted to. So gamma prime is the graph of F restricted to V. Yeah, we have this gamma prime. It projects to V, projects to Y, and well, and this is F. And this is community diagram, but this is isomorphism, so we obtain the desired. So F was only rational, but we see that it's actually regular. It's the composition of the inverse map and this projection to Y.
Игорь, вот из этой диаграммы как видно утверждение неравенства на размерности, которое было?
It was only lemma, right? And now we have to finish the proof of our theorem. Namely, we need to know that dimension of the projection of this bad set is at most dimension of X minus 2. And this is true because dimension of X is the dimension of a graph and is bigger than dimension of the bad closed subset. Yeah, because it's irreducible and it's strictly smaller closed subvariety, and this is bigger than dimension of pi of B plus 1, right? Because the fibers were at least one dimension. So the image has dimension at least one less. So we are done. Okay. Welcome. Fine.
Можете, пожалуйста, какой-нибудь пример привести, когда
Yes.
рациональный морфизм вот такой не продолжается?
Oh, certainly. Yes. A very stupid, most stupid example. We have x is just plane, or I don't know if you want, maybe if you want a projective, maybe let's take projective plane, and y is the blow up at 0. Okay, and you have a morphism like this, like f inverse, but you have a rational morphism back f, and f is regular on the complement p2 without the origin. Okay.
Спасибо.
Welcome. And so let me just say another truism. So this is well, this explains why all the morphisms between.
В проективном пространстве разве входит точка 0? Это...
Oh yes, but you may call it any other name you like, not necessarily 0. You may call it Michael or Sergey, whatever, any point you wish. So while the morphs between smooth projective curves are given by the embeddings of their fields of rational functions. Because for curves in dimension 1, rational is the same as regular. Because the irregularities occur in codimension 2 or higher. Yeah, you can extend through divisor, and that's what we know from curve. Okay. Okay, and that's really a very powerful statement. I'll have to stop now, but next time we will have some application of this powerful regularity in codimension 1 statement. So it will allow us to classify algebraic, one-dimensional algebraic groups. Okay, well, we all know that they are additive group, multiplicative group, and elliptic curves. And next time we'll rigorously prove this, deduce it from this regularity in codimension 1. Okay, so that's it for today. Any questions?
Am I right that by this reason, for curves, the notion of normal is the same as smooth?
Yes, absolutely. Yes.
What book do you recommend for geometric Lagrange program?
What book?
Yes, our reference or survey paper, whatever.
Well, there was one book that is called An Introduction to the Langlands Program. It was, well, at least one of the editors was Denis Gaisgori.
Okay.
But, well, there are vastly many books like this. But maybe it makes sense first to learn some algebraic geometry and some representation theory beforehand.
Thank you very much.
Welcome.
Okay, and
yes.
Can I and this proof of Grothendieck theorem for P1, does this proof extends or gives some help to prove in higher genus, or the proof for higher genus is absolutely different?
No, but there is nothing to prove in a sense. It's not true that in higher genus any vector bundle is direct sum of line bundles.
Yeah, I mean
decomposable vector bundles of any rank.
I mean to classify bundles, line bundles.
But
over.
I don't know what does it mean to classify. Say for elliptic curves, maybe there is some more or less explicit classification, if you want.
To describe modular space of.
So for elliptic curve, in a sense, you can describe the parameter space, but for higher genus, no way, absolutely, it's out of question. There is no way to.
There is a notion of modular space of
yes,
locally free shifts.
Right, absolutely, but there are no coordinates there. You cannot introduce some, so to say, even rational coordinates, birational coordinates. I mean,
you said that this is
rational, but still you can describe it in terms of powers of elliptic curve. But for higher genus curve, you cannot describe it. Like, for example, you know that the Picard or Jacobian variety is rationally is just like symmetric power of your curve, but nothing like this is true for vector bundles. It's true for line bundles, but not for vector bundles.
А вообще на проективной прямой, если возьмем два векторных расслоения, у них бывают эти нетривиальные расширения?
Oh, yes, absolutely. Yeah, for example, you can have 0 goes to O of -1, goes to O plus O, goes to O of 1. And this will be non-trivial act from O of 1 to O of -1.
Понятно.
Yeah.
Okay, and I also have a question about so you said that I mean what we study next. I heard that there are some such things as K3 surfaces and del Piazza somehow.
Yeah.
Yeah, and
I did not plan to study surfaces, unfortunately. Well, there was a course given by maybe Kostya Shramov, yeah, or maybe it is still being given now. I'm not sure. So I will not repeat this.
Okay, thank you.
Oh, sorry. Okay, so let me save the note. Stop the recording.